Thank you for coming back. Thank you. Thank you.
So we were going to do a panel, but instead we're going to ask everybody to remove your shoes. No, we're not. Let's just do the panel. Okay. Let's see what happens when I click this. Okay, that's good. Okay. So I'm just going to introduce it. This is really about two folks who are at the edges of doing some extraordinary work and rather urgent and important work around the urgent invisible. The invisible, broadly speaking, is everywhere you look and has been a topic of inquiry for a long time. But for, basically thousands of years, the practice of science was delegated to things that were visible. And that's basically what scientists worked with. They worked with things that were visible. And then they started inventing and evolving tools so that they could see smaller things or further things, or they could see things better. And so there was they invented a telescope and a microscope, and that gave you hints about the moon and hints about the very first aspects of DNA. And then computation changes it all. So whether it's the Large Hadron Collider at the micro or the James Webb Telescope at the macro, it allows us to see things that just simply have no purchase for the eye under normal circumstances. And then lately, if no one has noticed, the invisible has begun to grab the headlines. So this is a shot from California. This is what California looks like, in fire season, basically. And the ability to sense what's in that air becomes urgent. And generally speaking, what we learn doesn't come from, like the government. We're sort of left to our own devices. This is Purple Air, which is a portable air sensor. It's a couple $100, and we are gathering huge amounts of data about what's actually in the air, not from the Environmental Protection Agency, but rather from lots and lots of these tiny little distributed sensors. And this is true no matter how urgent the invisible becomes. So this is Fukushima, 2011. Where it was basically impossible to get radiation data from the Japanese government, and that's why Safecast started up at that time. There's a bunch of researchers who just basically kind of figured out how to hook up the cheapest possible way to detect radiation, and they were able to generate what evolved to become very, very precise and very, very important maps of the radiation in the Fukushima exclusion zone. The same stuff that they worked on is in use right now. This is data from the Chernobyl exclusion zone in the Ukraine. So these things that sort of evolved for one circumstance get used for another. And then, of note, 6 years ago, I was here at DLD, and I gave a talk. I gave a talk about how it was possible. At this time, I was using bees to gather. It was possible to start to identify what the life was around us, the invisible life around us. And so we would use bees to gather the data, and this is what the data looked like, and it looked like this, and it looked like this, and it looked like this. And the thing that's interesting from 6 years ago is this part where a lot of what we would find were sort of these no-name viruses. And I would say that the main difference between 6 years ago and today is that now these viruses have names, and we know them. We all know them. And that's because the world has shifted in these radical ways, and because what was a sort of like casual investigation is now very urgent and important. I've started working with Elizabeth at Poppy, which you can see one over there. You can see one here installed in a theater, on a boat, in a factory. And we're going to learn more about what that's about. But this is basically the ability to sense pathogens, viruses, anything that's deleterious to human health and outcomes in the air itself. And that's driven basically by this unhappy curve that we're all familiar with. And as it moves further to the right, it just becomes more and more urgent. And then I say that because there's this other curve that I think is less well known, and this is the methane emissions curve. And Ari will get into it, but you may not know much about methane emissions. You're about to find out a bunch about it, but we don't want that number to go up. Is the point? It's just not in our collective interest. This was a New York Times story about it, that methane's emissions had soared to a record in 2021. And in the New York Times, they used an infrared camera to visualize the methane emissions, which is like, you can do that, but that's not really a very efficient way to do it. And so what we're going to learn about is, number one, what methane emissions are, and number two, why it's so important to be able to see them. So these are sort of like the two curves, the curves of how viruses are spreading and globally and in any given room, and how methane is leaking. And the ability to see that is absolutely like the first and possibly one of the most difficult steps in actually being able to address it. So first up is Ari Gesher, CTO of Kairos Aerospace, and to talk about methane emissions and the ability to see them.
Thank you, Kevin.
Yep.
It's really great to be here at DLD. I'm the CTO of Kairos Aerospace. We're like a rapidly growing startup in Mountain View, California. We use a mix of proprietary sensors that we build along with bursty scientific computing to help oil companies pinpoint the places where they're actually generating methane emissions out on their oil fields. So I'm going to show you how all that works, but before that, I want to give the quick sort of climate crash course. Someone removed the word course from my slide.
No, it wasn't me. I saw that and I was like, wow, that's aggressive.
Wow.
Like, yeah.
I'll take it. All right, climate crash. So we're all familiar, hopefully, with graphs like this showing the concentration, the atmospheric concentration of greenhouse gases. And the gas that gets the headline on everything is CO2, and CO2 is a very big problem, but methane is sort of has a very strong supporting role in the global warming that we're seeing. So, and there's some really interesting differences between methane and carbon dioxide. So, on human timescales, carbon dioxide is in the atmosphere forever. As soon as we put a molecule in, we got to figure out how to take it out. Methane is not that way. There are natural processes that remove methane from the atmosphere. It has a half-life of about 12 years. Most people just kind of pencil that out to say it's there for 20 years and then you can forget about it. And the other difference is that methane absorbs 84 times the infrared energy that CO2 does when it's in the atmosphere. So it's a bit of an accelerant. It's like pouring gasoline on the fire of global warming, and it speeds everything up. But because it removes itself from the atmosphere, all you have to do is put less in the atmosphere, and the level goes down like on its own. So because it's such an accelerant, and it'll remove itself from its atmosphere, it's a place of low effort and high impact to mitigate climate change. And if we look at the various sources of climate change, there's many sources of climate change. The sources of methane, there are some natural sources. There are some now sort of quasi-natural sources, like is human-caused climate change responsible for the forest fires? Are the forest fires natural or not? But we're going to put that down and look at the stuff that is purely anthropogenic. And that's about 2/3 of it is agriculture and waste, which is basically rice, cows, and rotting garbage. And then 1/3 of it is methane that leaks when we poke holes in the ground and take the oil out. So it's leaking oil and gas extractive infrastructure. And that's the place where Kairos is focusing on. This is a place where there's man-made infrastructure that can be repaired that will actually lower the amount of methane emissions. So our origin story goes something like this. 10, 15 years ago, there was a bunch of research that started, like, there's always been this discrepancy between what we can see in terms of methane coming off of oil fields with satellites and what we've measured or guessed, because there wasn't a lot of measurement, was going on the ground. And so there was this hypothesis called the super emitter hypothesis that actually the source of all these emissions were very small numbers of very large leaks on very geographically sparse infrastructure. And the only way you could find them is by building kind of a scanner to go look at everything. Brian Jones and Steve Diker, PhD astrophysicists who were working at Lockheed Martin, said, we could build an instrument to do this, but we're going to start a company to do this. So they left Lockheed Martin, started a startup, went into Brian's garage, and this was the early staff. So that's Steve in the back, and in the front you have Luna on the left and Kepler on the right, and Brian was the photographer. And they worked on prototypes of the spectrometer and sort of worked their way through it. We got to, this is the Mark IIA, which was our first production spectrometer, and it definitely worked in the lab and in controlled release tests, but you're always worried that when you take this out in the world, like, what if there aren't that many of these leaks? What if we're not going to see anything? Wasn't really an issue, turns out. These are some early pictures from our first campaigns of plumes. And then we went and said, let's build this up as a company. So I have a little video to show you. You might recognize the voice of the narrator, and it'll really explain the way that the whole system works. Because it's not enough to just have the camera. You need the entire system to gather, process, and deliver the data.
When we fly over the pincushion landscape, we observe leaks coming from facilities like wells, storage tanks, and buried pipelines, as well as from operations like active fracking sites and the loading of liquids for transportation. In order to image all these assets, Kairos uses detailed flight plans consisting of long passes of level flight that sweep our half-mile wide sensor track over our target assets, seen here in a Bay Area certification flight over a known local source of methane, a landfill. Switching back to an aerial visualization, we can see the sensor tracks sweeping across the landscape as the plane flies back and forth over the target area in overlapping lines of data collection. Overlapping passes and multiple surveys a year enable us to capture at least 2 images, sometimes more, of methane plumes emanating from leaking oil field equipment. Our flights depart from Odessa and Hobbs in the morning and fly to their survey areas. Once on station, they perform precision flying between sets of waypoints in an overlapping lawnmower pattern. As the light fades, the planes head back to base to deliver the day's take, roughly 300 gigabytes of spectrometer readings, optical imagery, and precision GPS data tracks. Back in their hangars, the pods connect to uplink laptops, which compress and upload the data for processing. In the cloud, our data processing infrastructure waits for data to arrive. In fact, it is just-in-time provisioned as each phase of data processing begins, giving us an ephemeral, horizontally scalable, and fully automated processing pipeline. The methane data begins its journey with a process called path separation, the separation of multiple overlapping ground passes into discrete, non-overlapping ground tracks that can be independently processed and rendered into plume maps. The optical data undergoes a structure from motion transformation. Enhanced with the exact position of the camera in space, it generates geo-rectified imagery covering each of the target areas. Concurrent with the processing of optical imagery, the methane data moves on from path separation and enters the signal retrieval phase, a highly parallel numerical computation that compresses almost 2/3 of a year of CPU time into just 90 elapsed minutes. Combined with wind and ground elevation data from commercial providers, each pass is used to generate a stack of signal rasters that map out the precise location, shape, and volume of each observed methane source. Upon completion of each step, the results are pushed into an object store and indexed into our central geodatabase for later use in analysis and reporting.
So when we get to that reporting step, we know a lot more about each one of these plumes. So we know where it is, of course. We know what asset it's tied to because we get a database of assets from our customers, and we can tie it to the asset that's the source. And most importantly, we know how much gas is in that plume. We can actually measure the volume of the gas in the plume, and when we combine that with the wind speed, it tells us the actual flux of the leak. And it's not just about a single plume, it's about all the plumes. And so it lets us actually build up a map that looks something like this. It's from an early campaign in the northwest Texas, southeast New Mexico, Permian Basin area. And that's the location of all the super-emitters that we found. We didn't even check the whole map. You can actually kind of see the footprint of where we flew by where there are super-emitters, because they're pretty much everywhere you look. So this has an impact, like a real impact. So here's our impact numbers from 2020. We covered 13,000 square miles. We mitigated the equivalent of 7.3 million tons of CO2 entering the atmosphere, which is the same as 1.6 million cars. Last year, we covered a lot more ground, sometimes more than once. And thankfully, some of those leaks were actually fixed. But 12.1 million tons of CO2 mitigated, about 2.6 million cars taken off the road. So this is having a real effect. That said, we need to scale it up to global scale to have a really big effect. Going back to that inventory of where the methane comes from, the methane that comes from oil and gas infrastructure is going to account for something like 15% of the warming that the Earth experiences in the next 20 years. It's a very short-term thing. Our instrument, because it only works on land and it can't see quite everything, only about 85 to 90% of the leak gas, will if deployed all over, 10% of climate change will have been mitigated with it. So it's something that we feel has a lot of urgency and a lot of realistic potential to make a difference. And the place we're going with it next is actually starting to bring in market forces to do this. So not only can we go find one plume for one operator or all the plumes for a single operator, but we can actually go and survey an entire basin. And once we do that, we can actually build up a ranking of who's doing better and who's doing worse and exactly how much gas is being leaked or emitted by each one of the different oil companies. And that information, if it can be put in the hands of the various stakeholders, the investors, the people buying the product who are interested in a cleaner supply chain, can be yet another incentive for these operations to get clean. So we're going to keep working on it. We think we have a good start, but that's where we're at today.
Thanks very much. Yeah, great.
So Kevin, why do you make me go after folks like Art? I mean, seriously. I'm going to try and take it home here. Thanks so much, Kevin, for bringing me on the panel. My co-founder and I started Poppy back in 2019 with the mission to make the invisible visible. And what we were doing, much like Kevin's early work, was trying to make sure that all of the living things that we're sharing our indoor spaces with were known to us, and people could make decisions based on that. Like any good tech startup, we were in it to change the world, but 3 months later, after we started, the world changed itself. And I think we all know this image. We started by bringing biotechnology to buildings. So whether that was hospitals, whether that was cruise ships, whether that was long-term care facilities. But overnight, we realized that every indoor space needed Poppy, or something very like Poppy. But let's start with a question first for this room about what you are going to be ingesting in the next 24 hours. So what are you going to bring into your body in the next 24 hours? The easy one is water, so probably about 2 liters worth of water. You're probably not going to think about what's in that water, whether it's safe for you or healthy or anything else. You're pretty used to knowing that there's a lot of systems in place to make sure that you're drinking healthy water, most of the places, most of the time. You're also going to ingest about 2,000 calories of food. And everybody knows, even though we don't think about it a lot, there's this whole system regulating the supply chain with consequences and inspectors, and people making sure that what we then eat is also healthy or safe. But let's talk about air for a second. We'll talk about your air first. Outdoor air. How much outdoor air are you going to consume? That's about 1,000 liters of outdoor air. So 1,000 liters of outdoor air, again, lots of improvements to be made, but generally, most places in the world, we're not too concerned about breathing it. What about indoor air? Anybody might recognize this from the US as the DMV, which is sort of my idea of a nightmare of an indoor space. But it's essentially indoor air, because of so much time we spend indoors, 90% of our time, we're going to breathe in the next 24 hours about 10,000 liters of air. And what's in it? What's living in it? And I'm not talking about how much dust there is per million particles or anything else. What viruses, what molds, what bacteria is in what we're breathing, in the air that we're breathing on a regular basis. And so what we've been doing in a space like this, thank you for the wonderful LiDAR scan, Kevin, but this is a space like this. What we do is try and make it visible of what's actually going on in the space here. What pathogens are actually here and how they travel. So it's really about a couple of different things that I'll talk about. First of all, the White House came out 2.5 years into the pandemic and finally said, I'm going to quote here, indoor air quality is the single most important thing we can do in order to fight airborne infectious diseases. And we have to make sure that we're planning for it when we're managing our buildings and when we're designing our buildings. So that's great. 2.5 years in, finally, the recognition, COVID is a disease of the indoors. Unfortunately, what also didn't get said on that call, or the only thing that was really said in this announcement was that the main thing we should do is bring outdoor air inside. But there were no announcements about regulatory agencies. There's no guidance about what was safe and not safe. There's no inspection system that was announced as well. And really comes down to a couple of simple things that we've probably heard a lot over the last little while about how far apart we should be spending from each other. So what we've known for a little while at Poppy and really just has been reinforced is that the people who are responsible for communities, whether it's a group going to a conference like this, whether it's somebody who runs a hotel, somebody who is responsible for an office or a company where people work, we're going to need the tools and the ability to take actions based on real data to make those spaces safe. There's nobody coming in order to tell us exactly what to do or to do it for us. And so here's an example of a Poppy in a space. What we can do is using, essentially a lot of the same technology that you would be used to if you were going to go for a test at the doctor's, to test your blood or to test your saliva. We essentially can use things like DNA sequencing, RNA sequencing in order to understand what's going on in the air around us. And so lots of those have scary Latin names, but the wonderful thing is it's sort of an all-in-one solution to basically being able to tell everything here that's either DNA or RNA based. So this is what's going going on, and this is what we typically see in any of our customer sites, of all of the things that are going on in the background. Some of them, there's a normal background level, perfectly safe. Some of them, you don't want to see any of it, and that's where we help you spring into action. So lots of great data comes out of there, and thanks to a lot of Kevin's work, where we've been able to take this in order to help people understand what's going on in the space, but also how pathogens move in that space, is using images like this and data like this. So if somebody was sitting at the back of the room here, and unfortunately they had any kind of virus that they were breathing out, we can basically use these types of maps for those spaces and show exactly where there's hot spots, how long it takes to get cleared from the air, and basically help people make informed decisions on how to improve those spaces. So here's just another view of an office that we did. This is really not where you want to sit.
Yeah, don't sit there.
Yeah, the red arrows give that one away. Do not sit in that
Don't
corner
sit.
office.
That's a terrible place to sit.
There's so many people who've been doing so much important work throughout the last couple of years, and even before that, in order to make sure that we're breathing in good air, but they haven't had any way up until now to actually measure it. They haven't had any way of now to know if, the millions of dollars they're investing to redo the trading floor of their, Midtown Manhattan investment bank, or the teacher who's making DIY boxes for their grade 2 classroom. They don't actually know the effect of those. And a lot of the time, the spaces we go into are very well taken care of and are over-ventilating. So for example, there will be spaces where we'll tell them to bring in less fresh air because it's very costly, it uses a lot of energy to heat and cool that air, and they will maintain a perfectly safe level. So this is about making sure that we don't continue in the spiral and the cycle that we've been in. But, of course, it's not just about coronavirus, unfortunately. It's also about influenza A, influenza B. It's about things like Legionnaire's disease. It's about things like avian flu and, unfortunately, things like monkeypox. And it's also about a whole bunch of things that won't make us sick if we breathe them in, but could affect our health in the environment. So the air makes a great sampling medium, for example. So if there's something like salmonella on a surface, if you flush a toilet, turn on a tap, walk by a desk, you're bringing that all up into the air. So we can detect all of that as well. So where are we going from here? Our goal is to get to 1,000 infection-resistant buildings, and then 10,000, and then 1 million infection-resistant buildings. Because if that's the infrastructure that we have, that's the network that's out there, nobody will be worried about breathing indoors again and spending time indoors again. And hopefully, next year, when we're back in this space, we'll be able to tell you just how safe it is, and you'll be able to know that by about a lot of other spaces that you've spent the year in. Thanks very much.
Thank you.
Good time.
Do we have time for a question, or is there anyone to?
How close to real time is it? I mean, what's the latency?
Yeah, it really depends on what we're looking for. So we've basically focused on having very fast results for things like COVID, and then there's longer results if you want the sort of the broader results of any living thing that could be in it. So.
I think in general that one of the questions that people ask when I describe either of these works is, well, so what did we do before these capabilities? There must have been other ways to sense this.
Yeah, the way that methane has been measured traditionally is with what's called a bottoms-up inventory. And the way that you do this is that you make a spreadsheet of all the components on your oil field, and you multiply it by the number of components and their lab-established leak rate, and then you add up all those numbers, and then that's what you tell the EPA. This is how much methane we're leaking. So if you're wondering where's the measurement in that process, there is no measurement in that process whatsoever. And this notion of the super emitters as these sort of weird outliers is the thing that has been the reason this has not been balanced. There are some other efforts to do wide area measurement in this way. We're not the only ones doing it, but it's a new thing, and I think a lot of it has to do with having enough computing power to be able to process this stuff.
Just very quickly, there's a lot of folks who've been doing indoor air quality, but talking about the kinds of things that aren't living. Unfortunately, those are not the things that actually have shut down world economies and killed many, many, many people. And other than that, in specialty environments, so like hospitals, there's been very old school ways of checking for just a couple of different things, like MRSA, swabbing surfaces, sending those swabs to a lab, getting them on a petri dish, counting how they grow over a couple of days. But really, we've moved beyond that for so much of the biotechnology we use on humans. We now can move on to all the biotechnology we use on buildings.
Good. All right. Thanks to you both, and thanks to everybody here. Thank you for coming back. Thanks. Thank you. All right.